How is ReLU able to design complex non-linear patterns? This is a doubt that you can have because ReLU function looks almost linear. Then how is it even possible that a function that looks almost linear at very simple designs something very complex and very non-linear? Because the whole purpose of your neural network, a lot of layers, is that you should be able to design complex non-linear patterns. And I'm saying you can use ReLU as the activation function, and activation function is the component which introduces non-linearity. If such a simple function, that is a function that looks almost linear, how is it able to introduce the complex non-linearity? This is what we are going to discuss. First thing I'll do is I'll draw the graph of ReLU. That will be easier for a lot of our discussions. Also, you will understand how simple it is. We already learned about ReLU in previous lectures. Here we are just having a recap. On the negative side, it is always 0. So the graph will be something like this in the negative side. On the positive side, it looks like y equal to x line. This is how it goes. On the negative side, it's a straight line on 0. And on the positive side, it is a straight line y is equal to x. Next thing you want to understand is, okay, here I'll mark this as the x-axis. This is your y-axis. And this is the point at which behavior changes. Here, this is not a linear function, but this is a piecewise linear function. What is a piecewise linear function? If you see this piece, that is the piece before 0 on the negative side, this is a linear function because it's a straight line. Similarly, on the positive side, this piece is also a linear line. So you have two linear lines, linear functions, which are combined here. That is why you call it as a piecewise linear function. So ReLU is a piecewise linear function. Next question is, if it is a piecewise linear function, surely it is not a complex non-linear structure. For example, if you take sigmoid, it has a structure like this, S-shaped. Looking at this itself, you will automatically imagine how this can help you in designing complex patterns. Similar was the scenario with TANH as well. It also had the sigmoid shape, but ReLU is not like that. It is having two straight lines. Automatically, your mind may start thinking, how can this form complex patterns, right? So let us understand how this is working. First point you have to understand is, we already discussed that it is not linear. The reason for not being linear is this particular point, the kink at this point, which is diverting the line. This is the reason why ReLU is not non-linear. Still keep in mind, it is not strongly non-linear. You can say it is piecewise linear function. It introduces a bit of non-linearity. What you have to understand here is, in your neural network, you will have a lot of layers. And in each layer, you will have a lot of neurons. This is how it will work. In each neuron, your ReLU activation, it will bend the data space. This is what is happening. So at this neuron, let us say your ReLU did bend the data space to some extent. Then this neuron will again bend, and these bends may be in different directions according to the scenario, according to your input and all those things. Okay. So when all these are put together, you will have a final shape which is very non-linear and capable of forming any sort of complex patterns. So how you have to see it is, don't see it as having a ReLU activation on one particular neuron and having some input which is going like this. That is not how you have to see. Instead, you have to see it as a combined effect of all these neurons, that is in all the layers. You say like this now, that if you put a bit of effort each day, at the end of the year, you will have a big result, because each day you are putting a bit of effort, then a bit of effort. When all this gets combined at the end of the year, you will have a lot of effort. Like this, when you have each neuron contributing a bit of bend, at the end of the layers, after it goes through all the neurons in all the layers, finally the combined effect of all those ReLUs will be good enough to form any sort of complex patterns. So this is how ReLU is able to design complex non-linear patterns. See, when we explain this, I'm explaining this logically to you. Actually, if someone asks you how is it non-linear, prove how it is non-linear. This is not the way. But the reason I'm explaining this way is no one is going to come and ask you prove why ReLU is non-linear. That's not the point here. The point here is I want you to logically understand how is this ReLU contributing to complex non-linear patterns. If you actually have to prove, the way is different. That is, you have to say that there are two properties. One is additivity, one is homogeneity. These should be followed whenever you want it to be linear. Additivity says f of x plus y is equal to f of x plus f of y. If this is not followed, it is not linear. If you just take an example, let us say x is equal to -1 and let us say y is equal to 8, something like this, or y equal to -8, x is equal to 1, something like this. If you add it, f of x plus y will be -1 plus 8, or sorry, 1 plus -8. This will be -7. What happens? F of x plus y is -7, but f of x plus f of y will be f of 1 plus f of -8. Sorry, here it is f of -7. So f of -7 will be 0 because for negative values, ReLU is 0. But what happens here? F of 1 plus f of -8, f of 1 will be 1, f of -8 will be 0. So this will be 1. That would mean f of x plus y is not equal to f of x plus f of y. Then you can say it is not linear. But this part you don't need. No one is going to come and ask you. But this part is required. You should logically understand how it is able to design non-linear patterns, complex patterns with this sort of a very simple shape. Okay, so this is how ReLU is working.